Hello everybody, and welcome to Half-Life and Population Growth Problems. We are going to be living in these two formulas here, one for population growth, one for half-life. So, in this video, you guys will see two chemistry half-life problems and two population exponential growth problems. So let's start off with the first. We'll do the two chemistry ones first, and then we'll do the two populations one last. So let's start off with some carbon. So it takes 5,700 years for an initial amount, A sub 0, of carbon-14 to break down into half the amount, or A sub naught over 2. Given an initial amount, A sub naught grams of carbon at T equals 0, in other words, this is our starting point, find an exponential decay model, A of T equals A sub naught, e to the kt, that gives the amount of carbon-14 at time t, where t is greater than or equal to 0. So we don't know what A naught is going to be. E is our number E. We don't have a K and we don't have a T, but that's actually okay. What we need to find is K, because we are going to input T and we're going to get stuff out. So T can stay T, but we need to figure out what K is. Well, how are we going to figure out what K is? We're going to use the information given to us up here. So we know that it takes 5,700 years to take however much carbon we had. Just think of A naught as any number. Okay, and it doesn't really matter. We're going to see we're going to get rid of it here in a second. So A naught times E to the K. Now we're actually given a time here. The time here is 5,700 years. So notice that we have everything we need except for K. A naught is actually going to go away right now, because if we just divide both sides by A naught over A naught, A naught over A naught. So what we'll actually end up is half equals E to the K times 5,700. Now how do we get rid of the E? Let's take the ln of both sides. So we'll do ln of 1/2 equals ln of E is going to cancel itself out, and we'll just be left with the K times the 5,700. Okay, I need K by itself, so I'm going to divide both sides. So we'll have ln of 1/2 divided by 5,700. And K will equal a very, very teeny, minuscule number here. So we'll do ln of 1/2 divided by 5,700, and that'll give us negative 0.00012. So this K we're going to keep. This is going to be useful. So what this means here is K is our decay constant. So A sub naught is going to stay A sub naught. So to answer A of T equals A naught times E to the K, which we now know is negative 0.00012, times T, and T is in years. So here is our equation. So for some given amount of carbon, we will output how long it takes to decay. Or, okay, give me an initial amount of carbon. I'll tell you after 2 years, and then this will say, okay, well, how much carbon do we have left then? It's an exponential decay model. So this is the answer for A. Now B, answer for A. Now for B, calculate the time required for carbon-14 to decay to 1/3. So our output here is we want to know, okay, how long, which means we're solving for T. And we don't know the initial amount, but it doesn't matter. 1, 2, 3 times T. How long does it take to get to 1/3? Well, again, as of what happened over here, our A naughts are going to cancel out, and we're basically trying to solve 1/3 equals E to the negative 0.00012 T. Ln both sides. Now we take ln of 1/3 equals negative 0.00012 times T. Now we're going to divide both sides by our negative 0.00012. So we would get t equals, let's see, when we take ln of a third, and we divide that by negative 0.1212, we get, and I'm going to round this to the nearest year, 9,155. So it would take 9,155 years for any amount of carbon to decay to the third amount of carbon that we had. Okay, so we're going to do this again in the next example. So let's try half-life again, except for this time the half-life is given to us. So the half-life of plutonium is 88 years, so they give us a T. Okay, so what this is telling us is that whatever amount of plutonium you have, in 88 years it'll be half that amount. Okay, the given initial amount, A grams of plutonium, find an exponential decay model that gives the amount of plutonium at time t again. So we know from this top sentence here that we are going to have half the amount of plutonium. So this is e to the k, t now is 88. Notice I have totally omitted the a naughts because they were going to cancel out anyway. So now let's solve this. So ln of a half is going to equal 88k because the ln undoes the e because they're inverses. Divide both sides by 88. So ln of a half over 88 will give us our k, and then once we have our k, we can make our exponential decay model. So ln of 88 divided, oops, sorry, not ln of 88, that'd be far too big. Ln of 1/2 divided by 88, there's 88. Our k equals negative 0.00, and I'm going to round 8. 008, almost 007. So our exponential growth model then is, so to answer A of t equals A naught, which is just saying give me some initial amount, times e to the k, which is negative 0.008 t. So what this is saying is that give me some amount of plutonium, and if you stick it into this equation and you tell me how many years, I will tell you how much plutonium will be left over whatever particular amount of time is that you give me, because we're decaying. Now for B, calculate the time required for plutonium-238 to decay to 1/3. So similarly what we did to A, so if we want the remaining amount to be 1/3 of whatever we started with, we again can just kind of ignore the A naughts because it doesn't matter how much we start with. We only care that there's a third left when we're done. So the A naughts would cancel out again. So ln both sides. Anytime you have something with E, always think that this is going to be an ln problem. Divide both sides now. Ln of 1/3 divided by negative 0.008. So that'll be our T. So if we plug that into a calculator, we would get ln of 1 divided by 3 divided by negative 0.008. Our calculator tells us that is 137 point some stuff, but I'm going to round, so we're going to say 137. So 137 years. So here is our decay model, and here is how long it would take for the plutonium to decay, to decay to 1/3 the amount. Alright, so that was decay. Now let's look at some growth and population growth. So we're going to do a similar thing that we did last time, in that we're after this growth constant. We're after the k. So we're going to plug in everything we know at first, and then we're going to find our k. So the population of the United States is expected to grow from 282 million in the year 2000 to 335 million in 2020. Find a function of the form p of t equals c times e to the kt that models the population growth for the United States. Here t is the number of years since 2000 and p of t is in millions. Okay, so what do we know? Well, we know that the starting amount was 282 million times e to the k, and then how many years went by from 2000 to 2020? Oh, 20 years went by. And after 20 years, we went up to 335 million. So P of T is the ending population, C is the starting population, E is E, K is the growth constant, which we don't know, which we're trying to solve for, and T is the amount of time. Okay, well, there was 20 years that went by. So let's solve this. So the first thing we're going to do is we're going to divide both sides by 282. That'll get us e to the 20k. I'm just going to flip this around a little bit. Let's take the ln of both sides. So equals 20k. I'm going to take the ln of 335 divided by 82. ln 335 divided by 282 as a decimal, 0.172. 0.172. So I ln both sides. Now we're going to divide this by 20 to get out k. So dividing both sides by 20, and we get 0.0086. Okay, with that as the k now, we can find our function. So to answer A now, P of t will be equal to big C, whatever you tell me your starting population is, e to the k, which is 0.0086 times t. Here t is the number of years since 2000. Oh, sorry, we actually do know c, don't we? We know our starting population was 282. Okay, so B says, assume the trend in part A continues. In what year will the population of the United States be 350 million? Okay, so if the population is now 350 million, equals 282 e to the 0.0086. What is t? I don't know, because the question is saying, well, how long? So that means we're solving for t. So 350 divided by 282. 350 divided by 282. This gives us 1.24 equals e to the 0.0086 times t. Let's take the ln of both sides. So when you ln 1.24, you get 0.215. So now this is 0.215. ln and e will cancel, so you'll get 0.0086 t. Now divide both sides by 0.0086. Divided by 0.0086, and we get roughly 25. So assuming the trend, what year? Well, it'll be 25 years, so that's the year 2000 plus 25, so that's the year 2025. That is when we'll expect the United States to be 350 million. So basically what we're doing here is we're taking all the information that's given, we're plugging these in. We're given a t, we're given like a c here, we're also given the p of t, and what we're doing is we're solving for k. And once we have the k, we kind of reorganize stuff. We make a growth model, and then we use the growth model to solve what we have in part B. And that's going to be pretty much it for every single problem that you see. Once you can figure out your growth constant or your k, you're pretty much good to go to figure out any other problems that they could possibly throw at you. So I hope that helped, and as always, if you guys have any questions, please don't hesitate to ask.